Okay, in this video, which is the sixth video in the series of on molecular substances and the attractive the attractive forces between them, in this one we're going to look at what are called London dispersion forces. Okay, now of the forces I've talked about so far, the hydrogen bonds and the dipole forces, London dispersion forces taken on an individual basis are by far the weakest of the forces. And to define these type, so any substance that has electrons will be London dispersion. That's the first thing that the viewer needs to realize. So that means that if you're a hydrogen bonder and you're a dipole, you also are a London dispersion force because you contain electrons. All right, now what is the nature of this force? All right, this is, and I'm going to abbreviate. Let me go ahead and put that in here so there's no confusion. I'm going to abbreviate London dispersion as LD. All right, so LD forces happen due to the random movement of electrons. All right, basically the idea is this. So I'm going to draw a circle. This represents some kind of nonpolar molecule. Although what I'm describing applies to any molecule, but we're going to focus the LD mainly in the area of nonpolar molecules because this is where, quite frankly, these forces are most important. And your nonpolar molecule, whether or not we're talking about like a noble gas, or we could even be talking about like a neutral 7A element like fluorine, chlorine, bromine, or iodine, for example. Those particles have got electrons in them, and those electrons are in constant movement. Now, remember that an electron has got a -1 charge on it, so when it moves, it essentially leaves a place that is electron deficient. So due to electron movement, we can have the following kind of random polarization happen, where the electrons are moving, and it's possible that we can have, the electron density shifted like this. And this is a random movement. It's an instantaneous kind of movement. It's a transient movement, meaning that it happens in the flash of a moment. And so if we have the electron density shift like I'm illustrating it here, then what's going to happen is you're going to leave part of the molecule or part of the atom, if this is a group 7A element, or a noble gas, for example, like argon or krypton, you're going to leave the molecule partially polarized. So if I do it this way and just put the charges in, the molecule is going to look like this. All right, and it's the kind of thing that's only going to last for a moment. But here's the deal with it. If this is next to another molecule, which it's going to be in the situations that we're talking about, then the molecule that's next to this has no choice but to respond to that polarization. You can't put a charged particle next to something else that's got electrons in it without the electrons in that particle responding. So what's going to happen is when this particle comes in contact with this particle, the electrons that are in this particle are going to shift away because of repulsive forces, and you're going to get a polarization that happens like this. And if we draw yet another molecule in here, perhaps it's sitting here like this, all right, this molecule is going to be polarized with respect to the molecule that it's next to. The point being is that these polarizations happen in short periods of time, you know, literally fractions of nanoseconds, and the larger these are weak forces by comparison to the hydrogen bond or the dipole, but here's where these forces pack a punch, and I'm gonna build you a list here. All right, the greater the surface area, the more electrons you're dealing with, the greater the molecular volume, the stronger the force. The stronger the LD. Okay? Now, let me give you a couple of examples. Okay, this is called N-pentane. All right, it's a liquid at room temperature. Liquid at room temperature. All right, liquid at room temperature. Notice that it's composed solely of carbon and hydrogen. This molecule is nonpolar. Let me get that thing written right. Sorry about that. So this is non-polar. So the LD forces here are really, really important for a molecule like this. It's the reason this thing is a liquid at room temperature is because of the total sum of all the LD forces that exist with this molecule. But there's some other factors that come into play with molecules that are London dispersion forces. So if you look at this molecule and you were to draw its Lewis formula, basically this thing resembles a long cigar. So I'm going to draw it like this. And remember back to the initial video where I talked about what defines the strength of an intermolecular bond. Structure plays a role in that, all right? So for your N-pentane molecule, since they're all essentially like long cigars, you can see the end effect of that is going to be that the packing of the molecules is very efficient because they can pack like this. And what they're doing when they pack like this is they're maximizing the surface area in which they come into contact with one another. So they're maximizing the surface area of the molecule. And because we have so many carbons that are chained together here, we have lots of molecules. So we have large surface area, we have lots of electrons. I meant to say electrons in that last thing. We have lots of electrons. We have, because the molecule is very long with lots of carbons, we have a nice large molecular volume. And as a result of that, the London dispersion forces are stronger overall because we have a lot of molecules, a large surface area, lots of electrons that can be randomly moved around, all right, and we can maximize the efficiency of those charges, all right. Another plate, let's see, very quickly, let's look at the noble gases. So if we start with neon, all right, and then we go to argon, and then we go to krypton, all right, let's talk about these for a minute. Because as we move down the group, the boiling point of these gases that are normally gases at room temperature, the boiling point of these substances and the melting points of these substances increases. All right, and the reason why, now remember, these are atoms, and again, this list here applies directly to the physical properties of these elements because the London dispersion forces are going to increase as we move down this group. And then a lot of textbooks are going to say this is because we're increasing the molar mass, which is true. But you need to lock in the idea that increasing molar mass, what it's doing is two things. It's increasing the molar volume in which electrons can move. And because we're increasing molar mass, we're also increasing the numbers of electrons. So as we move down from neon to krypton, the London dispersion forces are increasing, and they're increasing because we are definitely going up in molar mass, but the main contribution of that issue is that we increase the molar volume of the atoms, and we're increasing the number of electrons. And so as we go down this group, the polarizability is increasing. Polarizability, sorry about the spelling. The polarizability of the atoms, excuse me, not molecules, of the atoms is going up. So that means the intensity of the charge differentials is increasing, which explains why the boiling point and the melting point of these atoms is going up. The same argument can be applied to fluorine through iodine. All right. Remember that fluorine and chlorine are gases, but bromine and iodine switch to more dense phases. The bromine is a liquid and iodine is a solid. And this change is happening because of what I described for the noble gases.